I'm in Brazil. It's been lovely. The sun's been nice, beach has been nice, food has been great. Cheese and shrimp is a thing, apparently. So yeah, I'm here today to talk about some recent work, assisted work distillation. But I'll start like everyone else seems to start, and I'll show you where Nottingham is. So Nottingham is in the center of the UK. So unlike other people, I can't really show you any pictures of nice beaches. In fact, our closest beach is Skegness, which is kind of a joke for the English people because it's not really the nicest place in the UK. But if you do come visit us, we will take you to some nice pubs. This is, yeah, see, people have been there. This is one of the 9 oldest pubs in the UK, whatever that means. Okay, back to the work. So assisted work distillation. This was done with a postdoc in our group, Dr. Ludovico Lamy and Gerardo Adesso. Brilliant. So if you get bored of me talking at any point, feel free to look at the archive instead. I need to point it. Okay, so what is the question that we're asking in this work? The question is, what role does the quantum feature entanglement play in thermodynamics? Lots of people this week have been asking this question in various guises. If I include all the citations of people who asked this question, obviously that would fill all the slides. But hopefully we captured and cited everyone in the actual paper. So the approach we're taking to this question is that in order to discuss something, you really kind of need to be speaking in the same language. And the language that we pick for this work is the language of resource theories. So the 2 resource theories in question are the resource theory of thermal operations. We've heard a lot about that this week. And the resource theory for entanglement is called local operations and classical communications, LOCC. So let me just start by kind of taking you through and introducing these two resource theories. I should be able to go fairly fast because we've, at least for thermal operations. So the resource in the entanglement case is any state, as you know, which can't be written as a tensor product of states which are locally owned by a party. And the resource in thermal operations is any state which can't be written as a thermal state with respect to some temperature beta here. So this is something we're hopefully all familiar with. The other ingredient for our resource theories are free states. So the free state in entanglement theory are separable states. So states which indeed can be written as a tensor product of the 2 local states. This is obviously just for pure, but a similar thing holds for mixed. And the free states in thermal operations are indeed the Gibbs state, where again this beta is the temperature of the environment that the state is in. We get these things for free. Now, most importantly, the ingredients to your resource theory are the free operations. So in entanglement theory, we are allowed to locally operate on our state, and we're allowed to communicate the result of that local operation to other people who hold a section of this entangled state. That's what we're allowed to do for free. And for thermal operations, what we're allowed to do for free is do joint unitaries on the system and Barth Hamiltonian, as long as, we have to do joint unitaries on the state as long as they commute with this Hamiltonian here. Obviously a statement of energy conservation. And the other thing we're allowed to do for free is get rid of the environment. We're allowed to trace that out. It doesn't cost us anything. Okay, and finally, just some measures in these resource theories. One measure for entanglement, this one only looks at pure states, is the marginal entropy. You trace out one of the systems, and the entropy then measures how much disorders that, how much, in a sense, information you've lost in doing that. And the measure generally at least in the asymptotic limit, for thermal operations is this value here, the relative volume and entropy. So this is the system we consider in this work. Alice and Bob share many copies of a bipartite state, and they also have a classical communication channel connecting the 2 states. So Alice, on the one hand, is allowed to do the LO from LOCC. She's allowed to locally operate on her state. Essentially, she has a lab full of infinite quantum instruments. She can do whatever she wants on her part of the state. She can break all the laws of thermodynamics in a sense that she wants, and then classically communicate that result to Bob. Now, Bob is, as is normal in the resource theory of thermal operation, he has some sort of and this dictates what his free operations are. And together, their task is to locally distill the maximum amount of work as possible. Okay, so the next question needs to be, what do you mean by Bob's work? Well, we've tried to be really explicit with this, and the way we do it in the resource theory of thermal operations is we have an explicit battery state. You'll see in a minute why the form of this battery state isn't so important in the derivation, but we append this to the system in order to help us describe what we mean by Bob's work. So this is what Bob is trying to do. He's trying to charge his battery state. This is just for a single round, but obviously the more zeros that go to ones, the more ease he has, the more energy that the battery has. So let's be a bit more explicit than this. So this is actually what we mean by work. Don't worry. I'll hopefully explain it. So we define the work as the supreme, R is the rate here. It's the rate at which you can make these, you can charge these battery states in the limit of infinite copies of the state, where obviously we restrict this act of charging the battery to thermal operations. And what we then show in the first appendix of the work is that if we take this result here, which is from the Resource Theory of Thermal Operations paper, the original Brandau one, it's not too difficult a derivation to show that this, in fact, equals this measure I was talking about, which is the relative von Neumann entropy here. And as you all know, it can also be written as the free energy. So I hope I've been really explicit with what we mean by work in this paper. You'll see that come up later. So, oh yeah, in case I forget something, yeah, essential point, this work takes the IID limit. It's a common kind of thing used in information theory. And this essentially is why we see no fluctuation relations in the result. Okay, this is just a value. It's not an expectation value or anything like that. So yeah, just to remind you of the setup again. We're trying to locally distill as much work as possible. So let me give you hopefully a simple example in which the correlations and entanglement present in row AB is going to help you increase the amount of work Bob can distill. So I'm going to use Ciliad engines in order to motivate this. As you know, the Ciliad engine, there's a particle in here somewhere. And in order to be able to, in a sense, distill work from this particle, you need to know what side of the engine this particle was in order to know which side you put your piston. This is the thing we use to motivate this. And like I said before, to be explicit about work, we can even stick a battery on this side here. But as you saw in the previous derivation, the actual the form of this battery state wasn't important in your measure for work. But if you wanted a picture, you could stick a bucket on this piston or something similar. So let's say, this state is maximally entangled. It's a pure state of these two engines are correlated. And let's say Bob doesn't listen to what Alice has to say. Let's say he just takes his state, we trace out Alice, and he's left with this incoherent state here on the diagonal. Now, as he hasn't listened to Alice, all the work he's able to distill, just for mathematical convenience, I've taken his Hamiltonian to 0, is the free energy of his local thermal state minus the marginal entropy of that state. Okay, so let's say Bob is willing to listen to Alice, and Alice does a measurement on her state, and she finds that the particle is on the right-hand side of her box, and therefore, knowing the form of the state, she can tell this to Bob, and he also knows which side of the box his particle is, and from which we can see now Bob's got a pure state and knows he has a pure state. He can distill an extra amount of work equal to the difference of this marginal entropy, and this will come up in a bit. Okay, so let's take it beyond examples and ask the proper questions. So the question is, what is the greatest distillable work accessible by Bob following a local measurement by Alice? Other people have asked this question as well and come to similar results. So we take the maximization over these measurements here available to Alice, and then Bob's state is conditioned upon the result of those of those measurements here, and she tells him the result of those measurements. Okay, so this is just a maximization problem, and it's using some basic information theoretic tools. You can show that this quantity here is exactly equal to this. There are some other papers that also show this as well. And the fact that this extra amount of work that we can distill is the Henderson-Vidal measure of classical correlations. So it's a measure of the classical correlations in the state rho AB. It's equal to the maximization over these measurements. So the next question, it's a question we don't think anyone's asked yet, is what if we let Alice perform measurements over tensor n copies? Well, what does this mean? It means something that's used quite a lot in information theory, and that is the regularization of this function. So Alice now has access to these tensor n copies all at once, at which she can perform a measurement upon. So the next question is this going to help Bob distill more work in giving Alice the ability to do this? Well, we can show actually this value equals the normal distillable work again, plus a quantity here called the distillable common randomness. Now, what this is if you give, essentially it's the amount of perfectly classically correlated states you can form using R bits of communication between the two parties. So you're trying to make the maximum amount of classically correlated bits from this state rho AB. So the question is this bigger than this? Does having access to many copies help? So we have the single copy case here with the Henderson-Vidal measure, and we have the many copies case here, which is a distillable common randomness. Now, what we do is we use a fundamental result from information theory. And that fundamental result relates the entanglement quantifiers, specifically the entanglement formation and the entanglement of collaboration, and these measures of classical correlation, the difference being the marginal entropy on, in this case, Bob's side. So for those who don't know, the entanglement formation is the minimum amount of Bell states needed, maximally entangled states needed to form this rho AB, and the entanglement of collaboration is the, actually no, I'll leave that point in a sec. So obviously we can rewrite the single copy and many copy case in terms of these entanglement measures. And the question therefore to ask is EC bigger than EF? Well, this is additive, but is this additive? We use another fundamental result from information theory, which is the non-additivity of the entanglement formation. This was a big open problem in the information community, took about a decade or so to solve. The actual proof for this is the logic of the proof anyway, is very, very interesting. I recommend having a look at the Hastings paper. Well, paper hasn't published it. But essentially shows the fact that the EF, through a very, very interesting proof, can't be additive. And therefore, we can also say that there does exist some states for which giving Alice the ability to measure over many copies of a rho AB state may indeed allow her to distill more work. Now, another essential point, this is because of the strange way in which the proof goes, is that although the non-additivity has been demonstrated, we don't know of any states which demonstrate it. They're probably quite strange, they're not qubits, but we definitely know that some exist. So it's up to you to take the strength of this statement as you will. So are there any more questions? What else can we ask about this simple setup we have? So far we've done, Alice has been doing a measurement, she's been then communicating that result to Bob, and then Bob has been trying to distill work from this. So what if we instead allow them to communicate, for Bob to talk back to Alice? Is this going to be in any way useful? However, as we've heard earlier this week, thermal operations are deterministic. Bob doesn't have access to these quantum instruments that allow him to do measurements on the state to tell Alice anything. So in order to really ask this question, we need to loosen the restrictions of Bob from thermal operations a bit. So the operations we're going to consider instead are Gibbs preserving operations. These are operations which the fixed point is the Gibbs state. And the only requirement, obviously you can see it's very loose, is that the Gibbs state goes to a Gibbs state. This is just to make sure that you can't distill an unlimited amount of work from anything that isn't a Gibbs state. Obviously it's quite easy to see that the example they use here is that to show that the Gibbs preserving operations form a larger set of operations than thermal operations, is that thermal operations are a subset of incoherent operations and can't make any coherence in the state, whereas Gibbs preserving operations can. But most importantly, for the sake of this work, is that Gibbs preserving operations can be non-deterministic, is that you can describe a Gibbs map in terms of quantum instruments on Bob's side of the state. So this enables Bob to tell Alice something. And the question we're now going to ask is, can this help Bob to distill any more work by talking to Alice? So the classical communication channel is open both ways, and Bob is now unrestricted to Gibbs preserving operations. So let's let them collaborate. And we define the work collaboration very similarly to just the normal work. Bob is again trying to get the maximum rate at which he can charge this battery. As you notice now, we've got Gibbs preserving operations, and again, this is in the IID limit. Here, okay. So this is the work collaboration. So as you can see here, it's quite a complicated quantity. You have to consider they can communicate infinitely, and it's over infinite copies, and the operations here are also infinite, and generally, you can't do a lot better than get bounds on this. So that's what we did, and we can demonstrate that this work collaboration, when they can both talk to each other, is upper bounded by the normal distillable work plus the mutual information in this case, which is as opposed to being a measure of the classical correlations, as you know, it's a measure of the total correlations of the state rho AB. Okay, so what's the difference? How has this helped? You probably are a step ahead of me, and you've recognized that the work of assistance plus the quantum discord equals in exactly this upper bound. So if we loosen Bob's restrictions from thermal operations to Gibbs preserving operations, it is possible, it might be possible, it's an upper bound, for Bob to distill the quantum part of the correlations of the state described by the quantum discord. A couple of caveats. Obviously, this quantumness of correlations that's distillable depends on the physicality of the Gibbs preserving maps to a certain extent, and obviously the validity of the upper bound. We're able to show the fact this upper bound exists, but it's very, very tricky to think of an exact protocol or indeed a state which demonstrates it. So there you go. This is essentially the story of the paper. We have the normal work of assistance. Alice does a measurement, communicates that result to Bob, and then Bob distills work. This is obviously, as we showed, using the non-additivity of the entanglement formation, is upper bounded by the case where we give Alice the opportunity to perform measurements over tensor n. And again, this is upper bounded by when we loosen Bob's operations to Gibbs preserving operations, and he may well be able to distill the full amount of correlations, in particular the quantum correlations. So some things happen if we consider a pure state. So far it's been completely general mixed states. And this is that the assistance measures become entirely equal. These measures of classical correlations coincide, and in fact just equal the marginal entropy on Bob's side. And for the case of the work collaboration, unfortunately that isn't the case. This thing is upper bounded by 2 times that quantity, 2 times the marginal entropy on Bob's side. So even in the case of a shared maximally entangled pure state, Bob can still distill an extra quantity of work there. Okay, brilliant. So we can almost go to the beach. This is just the conclusion. So first conclusion, is this a true statement? Quantum correlations are thermodynamically useful. I hope I've been particularly clear as to what case that applies for. We can definitely tell that the correlations are thermodynamically useful, in particular the classical ones. And I hope, oh yes, and the fact that these correlations might be indeed physically limited by the operations which you regard to be physical. And I hope I've also been able to demonstrate that the resource theory formalism is powerful. I mean, some of these results I've used took people a long time and a lot of thinking to solve them, and the fact we're able to use them to tell us hopefully something about thermodynamics is actually quite a powerful tool. And I hope I've demonstrated that today. So finally, is there anything else left to do about this question? So the question that I was asking yesterday after Mauro's talk is, why is this different from the Mauro Paternoster talk yesterday? Why were they able to distill this discord where under thermal operations I don't seem to be able to? Maybe this is the answer. It probably requires more thought and more chat. And the other question is, we can also consider the single shot assisted case. So as Giacomo was talking about in the IID limit, a lot of these things coincide with the stochastic thermodynamic community, but it's when we actually go down to the single shot case that some of these differences show themselves. So that's obviously hopefully the next interesting question we're going to attempt to answer. Okay, brilliant. I think I'm done. Good, I finished a little bit early. This is kind of what's left of our group. But yeah, thank you very much.
Nice talk. So operation, you have all these ideas of distillation, of work and so on, but